Principal component analysis is the topic for our video today. In the earlier tutorials, we had studied about dimensionality reduction. There are majorly two ways to achieve dimensionality reduction, but most of these techniques fall into these two classes called feature elimination, wherein we reduce the number of feature space by eliminating the features. And the second one is feature extraction. In feature extraction, we create, for example, 10 new independent variables where each new independent variable is a combination of each of the 10 old independent variables. Now, reducing the number of variables of data set naturally comes at the expense of accuracy. But the trick in dimensionality reduction is to trade a little bit of accuracy for simplicity. Now, when we keep as many of the new independent variables as we want, but we drop the least important ones. Because smaller data sets are easier to explore and visualize and make analyzing data much easier and faster for machine learning algorithms without extraneous variables to process. And that is why we do PCA. So PCA, please take a note that PCA is not any machine learning algorithm that falls under supervised learning or unsupervised learning or semi-supervised. No, it is a dimensionality reduction method, right? So this is the thing that we just covered. Now, well, principal component analysis or PCA is dimensionality reduction method, as I said, and that is often used to reduce the dimensionality of large data sets by transforming into a small set of variables into a smaller one that still contains most of the information of the larger set. So, in other words, principal component analysis is a technique for feature extraction, as we just did explain here. And it combines our input variables in such a way, then we can drop the least important variables where while still retaining the most important parts of the variables. Now, the main idea behind PCA is to figure out patterns and the correlations among various features. Because as we just did imply that we want to remove the least important, but we wish to keep the important variables. How do we find out that thing? We find it out by the correlations that we have. So on finding a strong correlation between different variables, a final decision is made about reducing the dimensions of the data in such a way that the significant data is still retained. So the procedure of PCA is quite lengthy and we'll be dividing it into various videos. In this video, we'll be studying the first two steps for PCA. Now imagine that this is the data that has been given to you. Now the first step that we have to do is standardization. Now, if you're familiar with the data analysis and processing, you know that missing out on standardization will probably result in biased outcome. And standardization is all about scaling your data in such a way that all the variables and their values lie within a similar range. Therefore, standardizing the data into a comparable range is very important. So we did do standardization earlier. We did it using standard scaler. You can go forward to the previous videos and definitely check that out video wherein we were talking about the different pre-processing techniques, right? So as the data has been given to us, let us do the standardization for F1 column. Now, so uh, let me just annotate and write simultaneously. So our x variable has 1, 5, 1. Please pardon the handwriting that I am having. And this is the x that we have. So if we add this, then therefore it is 10 and 20. So it will be 20. Number of variables that we have are 5. So 20 divided by 5 leads us to 4. So the thing that we have to achieve is standard scalar does what? X minus mu, which is a mean, divided by standard deviation, right? So this is what our x dash value will be. If we have to achieve this, how do we do this? So we found out our mu. Next thing that we have to find out is our standard deviation. So uh, yeah, yep. So the next thing that we'll be doing, let me just get back the annotations. Yeah. So we got a mu for our standard deviation. So x minus 4 will be minus 3. This will be 1 minus 3, again 1 and 4. Now the formula for standard deviation is what, if you recall, and as we are taking sample and not population data, so it will be x minus mu the whole square and divided by n minus 1. As I said, it is because of the sample data that we are taking. Summation of all and square root of the same. So my uh, x minus mu square. So this becomes 9, 1, 9, 1, 16. Right. So my standard deviation now is what? It is 36 divided by, so our n is here 5, we'll take n minus 1, which is 4, which leads us to 9, and square root of 9 is 3. So our standard deviation is 3. Now we'll be doing the scaling part, which is x minus mu divided by standard deviation. So it will be x minus mu, we already have done. You can look at this column, which is, now we just have to divide this column with the standard deviation that we are getting. So minus 3 divided by 3 is minus 1, and this will be 0.33 again. So it will be 333, and let's just take a round off, again minus 1, again 0.334, and for here we'll have 1.334, right? So this is how our whole standardization process will work, and this is just we have done for f1 variable. This is the same thing that standard scalar that we had discussed earlier under sklearn library works. So we'll move forward, and I'll just clear all these drawings. So this is what we were getting for the first one. Similarly, for all the data values, these are the mu and standard deviation values, and these are now our scaled data set that we have, right? So post this step, all the variables in the data are scaled across a standard and comparable scale, as we had discussed earlier. Now the next step in the process is of making a covariance matrix. So as mentioned earlier, PCA helps to identify the correlation and dependencies among the features in a dataset. A covariance matrix expresses the correlation between these different variables in the dataset. So it is essential to identify heavily dependent variables because they contain biased and redundant information, which reduces the overall performance of the model. So this is how a covariance matrix looks like. So if we find covariance between the same variable, that indirectly comes down to what we call it as variance. And this is how the covariance of the different variables looks like. And yep, so now let us find the covariance between the variables. So This is the scaled data that we have, right? And covariance is what? So it is x minus mean of x, and we multiply that y minus mean of y, and that is something divided by n, right? So this is how we find out covariance and variance. Now in the case of F1, let us just find F, so variance of F1, right? Let me just erase this and write it properly. Here, just a minute. Okay, so we'll be finding variance of F1. So covariance of F1 comma F1 is called variance of F1. So let us now first find what will be mean of these things. So just by looking at, we are understanding that mean will range down to 0. So it will be what? It will be minus 1 in minus 1 minus 0 this way, minus 1 minus 0 the whole square, and the similar way it will be it will be 0.33 minus 0 the whole square, and again the same thing repeating with all the steps. So if we just look, then it will come down to the point that it will range to 0.8. I hope that you are understanding. You just have to write 0.33 minus 0 the whole square. Similarly for this variable, similarly for this row, and similarly for this row. Now let us find and after finding the numerator, you just have to divide it by 5, and that is how you will come down to this point. Now we'll be finding covariance of F1 comma F2. Right. So now this is our x, this is our y. We found out that mu for this will range down to 0, and again if we just look at this data, it will again range down to 0 for the mean, right? So how do you compute over here? Now let us look at that. So it will be minus 1 minus 0 for the x value multiplied by minus 0.632. I'm not writing the whole number, but you can understand, minus 0, right? And thereafter you have to add it. So here there is a summation sign. So next it will be 0.33 minus 0, and again it will be 1.264 minus 0. I'm really sorry for the handwriting that I am having, but I hope you are getting. And similarly, we'll be doing for all the next rows, and you have to divide all the summation that you are getting. You have to divide it by 5. So after doing all of this, you will come down to a point where the answer that you will be getting is coming down to this thing. So 0.8 as we had discussed, right? So you can do all the further calculations. Now, what are the key takeaways that you get from this covariance matrix? So covariance matrix value denotes how codependent two variables are with respect to each other. Now, if the covariance value is negative in the case of this, right, covariance of F1, F2, it denotes that the respective variables are indirectly proportional to each other. It means that if one variable is increasing, the other decreases. Now, if it is positive, so in the case of covariance of F1, F3, So a positive covariance denotes that the respective variables are directly proportional to each other. So it means that if F1 is increasing, F3 is also increasing. So that is all that we'll be discussing in this video tutorial. From the next video tutorial, we'll be discussing the next steps for PCA.